So we're going to start out with this easy question. How far is it to Edmonton? 3 hours? Is that what most of you are thinking? And that's what's one of the things that's wrong with society. What did I ask you? I asked, how far is it to Edmonton? And you were all probably thinking 3 hours. That's maybe, on a good day, how long it takes to get there, not how far Edmonton is from here. But we as North Americans have this idea that when someone asks how far it is to somewhere, they want to know how long it takes to get there. And unfortunately in society, that's probably what they want. Here's the problem with that. Is time dependent on other things? Yes. Under ideal conditions, it might be 3 hours to Edmonton. It's not always. Okay? In the wintertime, there can be bad roads. Okay? We used to do a trip to West Edmonton Mall for Physics 20, okay? And we had a couple of times where it was 5 hours. We had one time where it was like 9. Okay? It was, yeah, we got really bad roads. Okay? Like really bad roads coming back. So it's not always 3 hours, but Edmonton is always about 300 and some kilometers from here. Okay? Unless the continent cracks open in the middle. Okay, between Calgary and Edmonton, it's going to be 300 and some kilometers to Edmonton from here. Right? That's not going to change. Right? So what we have to be mindful of in physics is what is being asked for. If a question says how far, they want to know in meters or kilometers or some other measurement of farness. Okay, how far something is away. Okay, not how long it will take to get there. We have to be very mindful of that. The way we describe distance and speed and stuff like that in our society is really messed up from a physics perspective. From a makes sense to us perspective, it's just fine. Okay? But from a physics perspective, it's completely wrong. Okay? And it can lead to a lot of frustration. Okay? I'll give you an example. A number of years ago, I was doing a backpacking trip with a buddy of mine, and we had been, it was our longest day. It was going to be like a 32-kilometer day, 2 passes up and down. It was a tough day. It was about 5 o'clock in the afternoon, and we'd been hiking since 6 in the morning. 50-pound packs on and whatever. We were beat, we were out of water, hadn't come across the stream for a while, and we're like, man, we should be at the campground. Like, we've been walking a lot and looking, kind of at the map and what we've been doing. We should really be there by now. Like, are we really this slow? We sat down and take a rest, look at the map again, and we see this guy just bebopping up the hill towards us, up the hill line towards us, and he is moving. Okay? And we see him, we're like, oh, sweet, maybe we can, this guy's coming the other way, so maybe he was at, Tumbling Falls Campground, and he'll tell us how long it takes to get there. It's like, dude, where did you come from? Tumbling Creek. Yeah, well, like, oh, awesome, that's where we're headed. How far is it? It's like, oh, 20 minutes. It's just 20 minutes down the trail. And the guy's barely breathing heavy, okay, mind you, it's going uphill like 5 times as fast as we were going downhill, okay. And we're like, oh, sweet, that's awesome. Put on our packs, 20 minutes, we'll be able to make dinner and get some water in us, whatever. And an hour later, we are cursing this guy. I mean, we are singing the 4-letter serenade like you have never heard, okay? And just like, we're gonna find this guy. We're gonna have some supper, and we're gonna go back on the trail. We're gonna find that guy in 20 minutes. And we're like, and then as we got some water in us and some food in us, and things started to make sense again, like, we're like, did you notice what he was wearing? He was wearing like army fatigues. And he was going uphill way faster than we were going, and we were going down. This is probably like a Navy SEAL out for a jog with his pack on. Okay, like, of course it was only 20 minutes for him. We're physics guys, both of us. Like, how did we not figure this out? Of course it was only 20 minutes. He was running. Okay, we were beat and walking. Okay, we're 2 out-of-shape teachers on their summer vacation, and this guy is just out for a stroll. But what did he tell us? Did he tell us how far it was? No, he told us it was 20 minutes. Yeah, sure, it's 20 minutes for the guy who, trains all the time and is in incredible shape and, is used to carrying an 80-pound pack as fast as he can while people are shooting at him. Like, yeah, of course he's going to be faster than we are. Of course, it didn't make sense when we were hungry and thirsty, but okay, afterwards, of course, it made sense. Like, that guy should have never told us how long. That's not what we asked. Okay? So it can lead to a lot of frustration if people are giving you kind of the wrong answer. Okay? Or they're giving you something that's dependent on some other variable, like speed. Okay? The answer he gave us was highly dependent on the variable of speed. Okay? Now, the reason for that is because of this relationship. Speed, which oddly enough we represent with v, okay, is equal to distance divided by time. All right? So, when he told us it only took him 20 minutes, that was dependent on his speed. Okay? The distance was going to be the same. He was going to travel the same distance we traveled in opposite directions. Okay? But the distance was going to be the same. But his time was different because his speed was much greater than ours. All right, so what we got to get out of today, understand that there are many ways of measuring how far apart or how fast objects are going. Okay? What we're going to be looking at is this in terms of scalar quantities versus vector quantities. Okay? Scalar quantities simply have a measured magnitude. Right? So time is a scalar quantity. Right? You never say it's 10 minutes right or 10 minutes left. Okay? Well, you might say there are 10 minutes left, but I mean like left, the direction left. Okay? We never say it's 2 years south. Okay? Like, that doesn't make any sense. Time doesn't have direction. Time only goes one direction. Okay? Unless you know something I don't. You have a time machine. Okay? In which case we should talk. Right? But time only goes one way, so it doesn't have direction. Okay? Speed also is a scalar quantity. Right? When you're driving down the Deerfoot, there are speed limit signs. Okay? They tell you don't go faster than 100 kilometers an hour. Okay? It doesn't tell you don't go faster than 100 kilometers an hour east. Okay? Deerfoot doesn't go east most of the time. Okay? Most of the time it goes north-south. Right? So speed is a scalar quantity. Distance is also a scalar quantity. Okay? It just measures how far apart two things are. Okay? Or how far you have to travel in order to get from A to B. Okay? There are vector versions of these measurements. Okay? Those vector versions are velocity, displacement, and time. Time is always scalar. Okay? If something has an arrow over top of it, it indicates that it's a vector quantity, which means it has magnitude and direction. Okay? So velocity still measures how fast you're going, just like speed does, but it also tells you what direction you're going. Okay? That's why there's never a velocity limit on a highway. It wouldn't make sense. Okay? The highway never goes perfectly straight. It always changes direction. You can't have a velocity limit on a highway. Okay? Distance and displacement both measure how far something is gone, but displacement tells you what direction as well. Okay? Now, when we start getting into the nuts and bolts of it, they are a bit different in how they express that. And that's what we're going to look at today. All right. So this formula, that one's going to be important, but it's on the back of your periodic table. Hopefully you still have that. Okay? There's a formula sheet on the back of that, okay? And you will find this formula on the back. So this is velocity equals displacement divided by time. Okay? We'll be using that. So there can be a little bit of algebra. That's okay. You guys can handle it. You handled the mole equation just fine. You can handle this just fine. All right. So if you've ever gone hiking off trail or done any orienteering, okay, you well know that the way we describe travel in everyday life is only effective at getting you hopelessly lost in a roadless or trackless environment. Okay? If you had somebody here who was not from here, had no idea of the geography of Alberta, okay, and they just wanted to know how to get to Calgary, and you said, oh, Calgary's really close. It's only 40 kilometers from here. Are they going to get there? Probably not. I mean, if they're somewhat smart, they can follow the signs and get there. But you told them Calgary's 40 kilometers from here. How many choices do they have for which direction to go? 360. Now, granted, Calgary's geographically pretty big. Probably 50 of those would get them there to some part of Calgary anyway. Okay, but not all of them will. Okay? Just telling them Calgary's 40 kilometers from here is useless. It's fine for us. We know where Calgary is. Oh, it's 40 kilometers north of here. Okay? But we know that. We know that it's north of here. We know to get on Highway 2 and go north. Okay? We know that. Someone who doesn't, that's going to be a pretty useless description, okay, of how to get there. All right, so sometimes it's okay to use scalar quantities, like on a road. Okay, none of the road signs that are on there that say, you know, Nanton this many kilometers or Lethbridge this many kilometers, they don't say which way because they assume you're going to what? Not so much no, but you're already on the road, right? They assume you're not just going to veer off, okay, and go 4-by-in through some farmer's field and figure some other way. Okay, they assume you're on this road, stay on this road. Okay, in that case, a scalar description like distance is fine, right? But if you're in a trackless environment, that's a little less useful. Okay, in this case here on this map, okay, if I'm here at Seldom Inn Campground and I want to go to here to Snake Indian Falls Campground, okay, there's a sign right outside of Seldom Inn Campground that says Snake Indian Falls Campground, 28 kilometers. Okay, what is it assuming I'm going to do? Follow the dotted line. This is a trail. It assumes I'm going to stay there. Okay, there is no sign that says Snake Indian Falls Campground is 21.2 kilometers at 60 degrees east of north. Okay. If I had a helicopter, that would be useful. But for me, on foot, going that way, while that number might be accurate, okay, it probably is around 21 kilometers, 60 degrees east or west of north, okay, this is not a way I want to go. These gray areas are glaciers. Okay, this is a mountain. Like I got to go over this river, which is a raging canyon. Okay, like this would be an impossible way to go. Okay? There would never be a sign that would say that. All right. Everybody okay with that idea? All right. So sometimes it's good to use scalar quantities, and sometimes it's not. They have their uses. All right. So if we say Calgary is 40 kilometers away, we make no reference to which direction that is. We just get on the road. We follow the road because the road takes us there. And along the road, that distance is 40 kilometers. Okay. So if I'm going from Okotoks to to wherever in Calgary, you can see that I changed direction a number of times. But in total, okay, the odometer in my car will say that I've traveled 40 kilometers. Have I actually displaced myself 40 kilometers? No. In a straight line, that location is not 40 kilometers from here. In a straight line, it's a little less, right? Because, I mean, you've all heard the expression, the shortest distance between 2 points is a straight line. It's actually wrong. The shortest displacement between 2 points, okay, is a straight line. Right? But you can see that I've got these little places here where I kind of go out to the side. There's curves. I change direction here. I turn to the west a bit. Okay? This line here that goes straight is shorter. And that's my displacement. But I would have to tell somebody who wanted to follow that line what direction to go, wouldn't I? I can't just say it's exactly this far in a straight line from here. Okay? Then again, we've got 360 choices for which straight line to follow. Right? I need to tell them, you need to go, 38 kilometers at, I don't know, maybe that's about 5 degrees west of north. Right? Something like that. Okay? I would have to add in that vector, okay, the vector or direction, okay, onto that quantity. Okay. So a scalar description, okay, again, only has a measured magnitude, kilometers, hours, kilograms, okay? All of those things are scalar quantities. Your mass is a scalar quantity. It's how much of you there is. It doesn't have direction, okay? Oddly enough, your weight does, because mass and weight are different, okay? Your mass is how much of you there is. Weight is how hard the force of gravity pulls on your mass, okay? So if I go to the moon, do I have less mass? No, I have the same amount of mass. There's just as much of me there. But it is the weight loss plan of the century because I will weigh 1/6 what I weigh here. Okay? Why? Because gravity is different. Okay? I don't get pulled down as hard on the moon as I do here. Right? So weight is actually a vector quantity and its direction is down, even though it usually goes up. All right. File that under dad jokes. Okay. So a more accurate, a more descriptive description. I think I changed it to descriptive in your notes, yes? Just check it there. I think I changed it to descriptive. I keep forgetting to change it here. Okay, a more descriptive description would be that Calgary's 40 kilometers away on a vector of 13 degrees east of north. Okay, now I'm saying here's how far to go and what direction to go in, and somebody would obviously be able to follow that and get there. Okay. All right, so let's look at a more common sense example here. And you might want to draw this somewhere in your notes just as our first example. So let's say I want to go from my house, which apparently has a slanted roof, okay, which is here, and I want to go to Home Depot. Okay. I don't know why I was going to go there. Okay, so can I go in a straight line from my house to Home Depot? I'm not telling you where I live. I can't. Okay, I can't go in a straight line because I don't live right beside Home Depot. Nobody does. Okay, there's a road at least between the nearest house and them. So I can't go in a straight line from my house to Home Depot. So I've got to follow the roads. There are no roads that are perfectly straight in line with Home Depot. So I've got to, follow Northridge Drive. Okay, and it kind of curves a little bit, and then I got to go across the river. Okay, so there's the bridge. It goes across the river, and then I got to follow, I don't know, Woodhaven or something over there. Okay. So I've done that. Let's say I'm walking even because it's summer and I want to get some exercise. So let's say that along that route, it's 4 kilometers. Okay. So I've walked 4 kilometers from my house to Walmart. Is that a scalar number or a vector number? It's scalar. That's how far I went. I went lots of different directions, okay? But that's how far I went. Okay, 4 kilometers. So that would be my distance. Let's say that takes me a half an hour. All right, so my time half an hour. How fast was I going? Eight. Yeah. I walked 4 kilometers in half an hour, right? So I'd walk 8 in an hour. Yeah. Okay. How did we figure that out? Speed is distance divided by time. Okay. I just went 4.0 kilometers divided by half an hour. That's 8 kilometers per hour. Everybody all right with that idea? Obviously, in a straight line, it's shorter. Agreed? Okay, so let's say that along that black arrow, is 2.8 kilometers, and we'll say let's see what number I picked here. I can't remember. 38. No, but it's north. Okay, well, I'm just going to say 38 degrees, and this is actually south of east. Okay? South of east. Okay? Because this, like, if you look at a compass, right? You're just trying to figure out where I live. There are a lot of places that are northwest of Home Depot, like everywhere. Because that's why I picked it. Everybody lives northwest of Home Depot if they live in the town of Okotoks. All right. So I'm going south of east, okay, 38 degrees. So this is a vector quantity. Everybody okay with that? Are we still talking about the same trip? This is me going to Home Depot. Okay, so it's the same trip, but that means my time is the same. Okay. What's my velocity? 5.6. Yeah. Okay. Remember, the other formula we had was that velocity equals displacement divided by time. So that means 2.8 kilometers at 38 degrees south of east divided by a half an hour. Okay? That means my velocity is 5.6 kilometers per hour, okay, at 38 degrees south of west. Okay? My velocity and my displacement should have the same direction, agreed? They're talking about the same trip. There, question?
Why does this happen?
Oh, I put west, sorry. South and east. I said east and I wrote west. East. Okay, everybody all right with that? Okay, so velocity and displacement are always going to have the same direction because they're always talking about the same path. Okay? All right, so these are both talking about the same trip. Okay, obviously in a straight line it's much shorter. Okay, if I had a helicopter, that's the way I would go. Okay, but I don't have a helicopter. I don't have a helicopter pad. Okay, none of that, right? So I can't go that way. But in the end, even when I walk this path, the black line is what I have done from a vector perspective. That's how far I have displaced myself in a straight line from where I started. That's the difference between distance and displacement. Distance is how far you actually have to travel to go from A to B. Displacement is your change in position. I have changed my position from here to here. So I have changed my position by 2.8 kilometers at 38 degrees south of east. Okay? There we follow the difference. Okay? Distance doesn't talk about your change in position. It talks about how far you had to go. Okay? Displacement is your change in position. Okay? And that's why one of them is vector and one of them isn't. Because along the distance, the red line, I changed my direction a whole bunch of times. Okay? All right. Here's where it gets even crazier. This part isn't crazy. I get to Home Depot and I realize I forgot my wallet because I'm old and forgetful. Okay, so I'm not going into Home Depot for the fun of it. So I just turn around and walk exactly the same route back home. When I get home, how far have I gone? Eight kilometers in total. It was 4 kilometers to Home Depot. It's 8 kilometers if I go there and back. Okay, so now my total distance, if I go there and back, okay, is 8 kilometers. Let's say that I did it exactly the same way. My total time is going to be 1 hour. Okay, which means my speed is still 8 kilometers per hour. Okay, would the same be true for the vector? No, it wouldn't be. Keep in mind the definition I gave you for displacement. It's your change in position. If I go to Home Depot and then go back home, when I get back home, my starting position and my ending position are the same place. Thus, I will not have changed my position. And from a strictly vector perspective, I will have accomplished nothing. Okay? Because I will be right back where I started. Okay? Which means my displacement will be 0 kilometers. My time will be 1 hour. That doesn't change. It took me an hour to go there and back. It was ended up back where I started. Okay? So then, what's my velocity? 0. Okay? Remember, velocity is displacement divided by time. And if my displacement is 0, my velocity is 0. This is where vector and scalar can really change. Okay? Even though I've walked 8 kilometers, from a vector perspective, everything's a 0. Because I ended up back where I started. Okay? If I only retraced my steps back halfway, then it'd be different. Okay? My distance would be 6 kilometers, but my displacement would be 1.4 kilometers at 38 degrees southeast, because I'd be halfway back. Okay? Everybody all right with that? Okay, so that's kind of, simple example of how that works. All right, so this is just the word version of what we just did there. Okay? So speed and velocity, okay, have this relationship. One of them is vector, one of them is scalar. Okay, we talked about your velocity for the trip would be 5.6 kilometers. Okay, 38 degrees. And then if you went the same route home, your total distance would be 8, but your total displacement would be 0. Okay, so it's important to understand that from a vector perspective, the same trip looks a lot different than it does from a scalar perspective, at least numerically. All right. Using v equals d over t, you're going to have to manipulate this formula. Because I'm going to say don't use the triangle. It's there to remind me, not that I need to remind you to tell you not to use the triangle. Triangles are stupid. Okay? All right, don't use a triangle. Why? Because you don't need one. Algebra is not that hard. Okay? Algebra is really easy, in fact. You only need to remember 3 rules. I went over those 3 rules in the chem unit, but don't worry, I'm going to go over them again because they're really, really important in this unit because you're going to be manipulating equations that are more complex than that. Okay? So let's start with this one though. Right now, it's set up to solve for v. I want to solve for d. So if I want to solve for d, what do I have to do?
The opposite operation.
Okay, the opposite operation. What am I moving? T. Yeah, I want to move t, so d is by itself. I need to isolate whatever it is I'm looking to solve for. Right? So I'm going to take t, and I'm going to move it over here. Okay, now what operation did I do when I did that? I multiplied, right? I multiplied both sides by t. Okay, so the t cancels on this side, and I've got t times v over here. You guys all right with that? Okay, that's the easy one. We learned how to do that one back in the chemistry unit with the mole equation. What if I want to solve for t? Okay, I can move the d over, but here's what will happen. What operation do I need to do to move d? Division, yeah. Okay, I need to divide by d in order to get d out of here. Right? So I'm going to divide by d. Okay, what's d divided by d? What's 2 divided by 2? What's d divided by d? 1. Okay. So that doesn't make d, I mean it makes d go away. It leaves a 1 here. Okay? And then I do the same thing with the other side. Is 1 over t same as t? Some of you are nodding yes, some of you are nodding no. Okay, I'm going to ask you this. Is 1 over 2 the same as 2? No, it isn't. Okay? It's a lot different. 1 over 2 is 1/2. Okay? 2 is 2. Right? They're not the same thing. All right, so even though mathematically I've kind of isolated t, I'm not solving for t, and I want to solve for t. So there's a little trick here. If I want to solve for t, I want it to be on the top of an equation. Anytime you solve for something, it needs to be on the top. Otherwise, it's 1 over that number. So what I'm going to do is the same thing we did just a minute ago. I'm going to multiply both sides by t. What do I do with v? Divide by it, right. Right now I'm multiplying by it, so I would divide. T equals d over v. Right? Now I'm actually solving for t. It's on the top of the equation. Now, what if you're not sure if you've manipulated something with it? Is there a way you can check? With physics, there is. Math, not always. Okay? But physics, there is, because we can check the units. All right? Let's say that my distance is in kilometers, and my speed is in kilometers per hour. Okay? If I divide these 2 units, what cancels? The kilometers. I'm left with, is that a unit for time? Then I did it right. Okay? You probably don't want to do that all the time. You just want to have confidence in your manipulation. But if you ever weren't totally confident in your manipulation, you could always double check by just putting the units in and seeing if you get the right units at the end. All right, so that's your manipulation for that formula. Okay? Now I caution you against something. First off, the use of triangles, they suck. Okay? The second caution is this. I see people do this all the time. I hate manipulating. So I'm just going to write all the manipulations of every formula on my formula sheet. That's all well and good until the test when you don't get your formula sheet and I give you a new one. And now you don't know how to manipulate equations and you are royally screwed. Okay? So we're gonna take some time and we're gonna learn to do algebra and we're gonna be just fine at it. Okay? Because there's only 3 rules we have to remember. Right? Now, these are other equations that we can manipulate. They're not hard. Okay? This is one we're going to be manipulating later on in the unit. Okay? But before we get to that, what were the 3 rules of algebra? Anybody remember from the chem unit?
Whatever you do to one side, you do to the other.
Right, that's the second rule. Okay, first rule was if I want to move something, I do the opposites. Okay. Okay, we only needed those 2 rules for the mole equation. We only need those 2 rules for v equals d over t. The third rule is going to be really important in this unit though. Okay, because we're going to run into formulas that are more than 3 variables. Okay, and so the third rule is, okay, to move what is not attached to what you're looking for first. Okay, move what's not attached first. Okay, that is the third rule. I know it seems like that should probably be the first rule because it talks about what you should do first. Okay, it's like saying to disarm this bomb, remove the firing pin, but first cut the wire. And like, you know, you should really have, I know, rule number 3 should be rule number 1.
Can we get an example?
I was just about to do the example. Yeah. Okay, you're way ahead of me. Stop getting ahead of me. All right, let's use this formula here. This is the graphing equation we're going to be talking about on Monday. Okay, y equals mx plus b. You're also going to do this if you're in math this semester. Okay. Let's say that I want to solve for m. Okay. So in this operation, I have that y equals m times x plus b. Okay. Right now, I'm trying to isolate m. So what's not attached to m right now? B. Okay. B is not attached to m. By attached, I mean you're either multiplying by it or dividing by it. You're immediately beside each other. Okay. So right now, b is not attached to m. So I need to move it first. I'm adding b. So to move it over to this side, I need to, all right, so I'm going to subtract b from both sides. So that's going to leave me with y minus b equals m times x. Now all that's left is stuff that's attached to m, namely x. Right? And I'm multiplying those two. So to move x, I need to divide both sides by x. So x divided by x is 1. What's m times 1? M. Good, then I don't have to write that. Okay? There. I just isolated m. Okay? Wasn't very hard. Just had to remember 3 rules. Okay? Move what's not attached first. Okay? And then do what's, if you want to move something, do the opposite. Do what you do to both sides. All right, let's try this one. That's a minus. This is a formula we're going to use later on in the unit. It solves for acceleration. I want to solve for VF. Right now, what's not attached to VF? Well, are these two kind of together here? Okay, like really, if I was doing this formula, okay, it would actually be like that. I should have written the brackets, sorry. Okay, if they're in brackets, they're attached. Agreed? Okay, what do I need to move first? T. T's not attached to VF. Okay, so I'm going to multiply both sides by t because I'm dividing by t in this formula. Is everybody okay with that? All right, so what's t divided by t? 1. All right, so I don't have to write the 1, right? Because anything multiplied by 1 is itself. All right, now I have t times a equals vf minus vi. Do I still need the brackets or can I get rid of them now? I can get rid of them now. Don't need them. Okay? All right, I want vf by itself. What do we do with vi? Add it to both sides. All right. I just manipulated for vf. Okay? Probably when you first looked at that formula, you had no idea how you were going to do that. Okay? But it's not too tough. Not too tough at all. You'll get to these and you'll have no problem with them. Okay? Before you know it, you'll be solving this. Okay, I want to solve for L. That's an L. The one on top is an L. Solve for L.
Oh, it's N.
Cursive, yeah. My cursive is worse. I almost used a curse to describe my cursive. Okay. All right, I want to get L by itself. L's under a square root sign. I don't want to find the root of L. I want to find L. What do I need to do to everything? Yeah, if I want to get, if I'm looking for something in its normal state, not its rooted state, I would do what to its root? Square it. Okay. See, if I want to do something, I do the opposite, right? Okay, so I'm going to square everything. What's t squared? T squared. What's 2 squared? Don't say 2 squared. 4. Okay. What's pi squared? Now you can say it. Pi squared. Okay, and now have I gotten rid of the root? Yeah. Okay, I want to solve for L. What do we do with G? Multiply both sides by it. What do I do with the 4 pi squared? Divide, yeah. I mean, I'm multiplying 4 times pi squared times L. If I want to move the 4 and the pi, I can move them together. I'm solving for L. I haven't done anything different than those 3 rules. Okay. All right. So there's the 3 rules of algebra. You can. And there they are again. I've done that slide like 4 times. Okay, let's look at this as our first example. I'm going to give you a minute to write it down. So all of you who don't have any paper up. Paper up. You got to write this down. Okay, also an important thing in this question. How far is a deer running at 15 meters per second travel in 45 seconds? Okay, what are we looking for here? Distance, right, how far? Not how long. They gave us how long, 45 seconds. This is one of those things. How far does not mean time. Okay? All right, I'll give you a minute to get that written down. So similar to how we solve mole equation questions, the first thing we want to do is write down the information the question gives us, our givens. Okay? So first off it says how far. That means I'm looking for distance. If it said how far and in what direction, I'd be looking for displacement. Okay? There aren't any directions in this one, so this is all scalar. Okay? So it says how far will a deer running at 15 meters per second? Okay, what did they give me here? Speed. Okay? I mean, it's distance over time, right? Meters per second, so that's speed. Right? So they told me what v is, okay? And it is 15 meters per second. And then it says in 45 seconds. What did they give me there? Time. All right, so those are the things that I know. I know v and I know t. All right, so that means I'm going to use this formula. How do I know that? How do I know that that's the formula I'm going to use? The answer is it's the only one that has the three things I have. Okay, I'm looking for D and I have V and T. It's the only formula on my formula sheet that has those three things in it. Okay, therefore I have to use it. So this is where you're going to use your like 4-year-old skills. Okay, matching. Right, so one of these things is not like the others. This is the one you need. Okay, because it's the one that has all the stuff you have. All right, I want to solve for D. So I need to get D by itself. How do I move T? Multiply both sides. Right now I'm dividing by T, so I want to do the opposite. Okay, so I'm going to multiply both sides by T, which makes it cancel over there, okay, and come over here. So T times V equals D. All right, so that means 45 seconds times 15 meters per second. Sorry, I'll have to put the units in. All right, now if I'm looking at this just from a units perspective, okay, this is meters times meters per second. Okay, everybody all right with that? Sorry, no it's not. How come nobody said anything? What's time measured in? Okay, so I got seconds on the top and seconds on the bottom. What do? They cancel, and what am I left with? Meters. Okay, good. So this is going to leave me with the right units. Okay, so 45 times 15. All right, 675 meters. Not terribly difficult. It's a little practice, no problem. Okay, any questions on what we did there? Okay, try that one. You're trying to solve for how long it will take a tortoise to crawl 200 meters at a speed of 0.25 meters per second. Because tortoises are slow. All right, I'll give you a few minutes on that one, then we'll walk through it together. Okay, so same as the other one. Okay, we want to look at how long it'll take a tortoise to crawl 200 meters. So we want to write down our givens. Okay, the 200 meters is a distance. Okay, and this is just something you have to get used to doing, which is when I read the question, I'm looking for, all right, that's measured in meters. Meters measures either distance or displacement. Okay, that's measured in kilometers per hour, or meters per second, or centimeters per year if it's a glacier. Okay, like something that's it's going to be distance over a time interval. That's always going to be speed. Okay, and this one they give me that 0.25 meters per second. Okay, and they're looking for how long. Okay, that's time. So V equals D over T. Now, as we said before, I don't want to solve for something if it's on the bottom of an equation. And right now, time is on the bottom of that equation. So I need to move it to the top. So right now, I'm dividing by T, and I want to move it, so I will. What's the opposite of divide? Multiply both sides by T. All right, so T's gone from that side. T now comes over here. But I want T by itself. So right now I'm multiplying by V. How do I get V over to the other side? Divide by V. All right, so T is going to equal D over V. That's going to be 200 divided by 0.25, which should be 800 meters. Sorry, seconds, not meters. 800 seconds. That's a long time. Go 200 meters. Okay. All right, everybody okay with that? If you were to ever get a question where the units didn't match, like let's say they made this can I divide 200 kilometers by meters per second? No. Okay, I have to make my units match. How many meters in a kilometer? 1,000. Kilo means 1,000. Okay? That's how the metric system works. Kilo is always 1,000 more than the base unit. A kilogram is 1,000 grams. Okay? Kiloliter, 1,000 liters. Kilo always means 1,000. Okay? All right. So in that case, I would have to convert the kilometers to meters. And obviously, this would be much, much bigger. It would be a very old tortoise by the time it had traveled 200,000 meters. That's 200 kilometers. Okay? All right. Any questions on how that one works? All right, let's get everything wiped down here, guys. So everybody, mask up. Go get the paper towel. Okay, if you need to use my spray bottle, go right ahead.